Welcome back. So, so I want to make you ex explain the vague term looks like random walk in a bit more detail and show one part of the proof, which is the capacity argument, which is which I think is nice. But let's start with making looks like a rigorous what I'm going to say is rigorous, but it's not completely what we use, but it's sufficiently similar. Yeah. No, it is a definition, just not the right one. Okay. So, but the assumptions are going to a little bit mimic this proof in the sense that we want to somehow be able to separate the past from the future. So the assumptions. So the first assumption, this is actually easy to state, is that that the heat kernel is approximately like the heat kernel of a random walk. So the probability, the W, remember the W is one, always I will use W for once reinforced random. It's already written here, so so always W will be the once reinforced random walk. But I'm not going to maybe so strict. I'm going to let myself have a little bit of a spare for this. So simple random walk has the probability to be at time t at any particular vertex is at most, okay, it's t to minus d half if you are in a good vertex, and then decays exponentially if the vertex is too far. And here I'm going to ask just, I'm not going to ask the decay. It's not, well, okay, formally, in the paper we probably ask the decay, but let's not bother about that. And I'm adding a little bit. I'm making my requirement a bit weaker. It won't matter for what we do. So this is one requirement. The other one is a bit more complicated. They will require 3 definitions in a row. Maybe I'll actually take my tablet for this. So definition 1, we say that lambda is will always denote a cube in ZD. So we say that lambda is good if that's not right. That's not written correctly in my notes, but okay, that's not your problem. If you intersect it, okay, maybe okay, lambda is this is an R to the D box, an R by R by R by R box. If this is no more than R to the, sorry, what minute, is no more than R to the 2, again, and again, I'm making myself a leeway. So for random walk, that's the typical amount that a random walk intersects a box. Normally, a random walk intersects a box of size R in dimension sufficiently high at only R square points. I'm going to put my leeway, a bit of leeway. So I'm going to ask just this, R to 2.5. Actually, I'm probably asking 3.5, but we'll see later what is the correct number to put here. So that's just the definition. So it's good. I'm just going to say good, but of course it depends on T and it's a random property. So some boxes are good, some boxes are not good. It's a random property. Okay. So if at a fixed T, so goodness will depend on T. Yeah, it's a T good thing. Yes. Now, yes. And here, okay, and second definition, T is relaxed if for every R bigger than 1, you look at, okay, I'll write and then explain. So you want that any neighborhood of the point where you are now is good. So if you look at distance 10, you have no more than well, 300 exactly. But also in a big, but it has to hold for every R. So you are not, it's, you don't have local problems with your next door neighbors, but you also don't have problems with your neighbors from the next country. So you are good with your neighbors in all scales. Okay, I'm not going to pursue the political analogies. And now you're, maybe I shouldn't have just erased it. And now you see that how these two things work together. If I know assumption 1, then at any relaxed time, I have a positive probability to forget about my past, because my past is not so thick, and the probability to hit every point is not so large, and the dimension is at least 5. So I have a good, every relaxed time, there is a positive probability to forget about my past completely. And now comes the requirement, and this is, I think, maybe the most important point in L-Bottom's time, is this particular formulation of looks like random walk, the probability that for any t smaller than t, there are lots of relaxed times locally in a very specific way. So the number of S's in an interval of size t to the epsilon, which are relaxed, is at least 0.9 that neighborhood. And this has to happen with very large probability. So this is the second requirement. So, and this is, we took it directly off of the paper of Dor and Aaron Sly. And I think maybe this is the most important novelty there, this particular definition. So let's again look at this for a second and see why it have to be like that. So you cannot ask for all times to be relaxed or anything. That's not true for random walk. Okay, this requirement goes all the way to R equal to 1. So some proportion of times will necessarily be not relaxed. So, right. You're not going to be mad about me about that, are you? Uh, but if this 100 is sufficiently large, then you can request that 0.9, and this is already, because we are looking at intervals which are not so large but not so small, then we can require that with very high probability. So epsilon is just a number. Epsilon is just 10 to the minus 4 in this requirement. So everything, and if you are looking at something which is polynomial in T, then you can request things to happen with probability bigger than polynomial. And this makes the analysis much easier. The fact that we always have to work we work with probabilities which are bigger than polynomials, so no problem on summing them over times, over space, over whatever. There are still some polynomial, but they are not but they are not exponential, so we don't have to be very precise when we finish the induction, right? It's easy to use and also easy to prove. So this is really super crucial to use something which is not polynomial, but not exponential either. So this is an induction, right? You need to prove what you can assume, what you assume.
It's on this particular test.
Yes, exactly. Yes, yes, exactly. So that's the assumptions. H1, H2. Okay. Um, okay, so now we have to prove that we get them for t, and we have to prove them for t plus 1. Okay, as I said, it's not going to be even a remotely a complete proof, but some ideas. So step one would be to, and always in this kind of proofs, you have at some point to increase probabilities to make your events more likely, right? Because you are making an assumption that only happens at a specific probability, but at t plus 1, you need to get something at a higher probability, at probability log square t plus 1. So this is bigger, this is smaller, this is it's a higher probability, so probabilities go to 1. So at some point you have to increase probabilities, whatever you do, and this is the point I want to contemplate. So the first step is to conclude random walk-like behavior. And I'm not going to give you any details of that because you have to choose something. Okay. So, and here in this step, there is no increase of probabilities. So basically, your assumption is holds in this probability, and you will get that the process behaves like random walk in many ways. I'm not going to even write which ones, with this probability or a little worse. It doesn't increase probability at this step. Increasing of probabilities happens in the next step.
Base, at the base of the induction, this is where the slowness of A.
Yes, yes.
But this is also, I mean, once you assume the base sufficiently small, this is easy.
Yes, yes, because if I sufficiently, this is all the base of the induction, for example, at time 1 or time 100, or I don't know which time we start. The base of the induction, these are all properties which are true for random walk. And if so, you want to do the induction at 100, you say random walk does that. Take A so small that up to time 100, you don't even feel the difference. But okay, so we know that, and now we have to prove this for larger t. And so we have to prove stuff, and here comes the part that I chose to speak about is the capacity argument. We are going to use capacity for this. So again, so what are we trying to do? We are trying to prove H2 is the more interesting thing, at time t plus 1. So we need to prove something for every r. And in fact, the argument, there are two different arguments, one for small r and one for large r. I'm not going to talk about the small r, just about the large r. So let's fix r, which is a little not so small. So let me just write what it is. Okay, maybe I won't even write it. Fix r not too small. No, it's a power of t. And we want to show, so, but just that before I start with what is a capacity, just what are we doing? We fix an R, which is the R from this definition. Going to be difficult to squeeze everything in this blackboard. Okay, which is the R from this definition. So we need to show somehow that that our process is not too large in any box of size R. So this is what we need to show. Okay. So let's start by remembering. So questions before I define what is capacity? Okay. So let's remember what is the classical capacity. So the capacity of a set A, okay, is simply the sum of escape probabilities of random walk. Okay, it's the sum over all A in A of the probability when you start a random walk from A. Always when I write A above the probability, that's the starting point of random walk, that R, 1 infinity, does not intersect this. Okay, so that's the definition. So let's try and get a little bit of feeling for that. So of course, the probabilities only come from the boundary, because the point is in this inside, for example, if all its neighbors in A, then this probability is 0, because this is we are requiring, okay, 1 is like the first step. So at time 0, it's in A. So it's in A, so I can't I can't do anything about that. But I want from the first step on that it's not in A anymore. So this is an escape probability. Okay, and in fact it is the same as for people who are more familiar with definition of capacity using kernel. It's just the capacity when you're defining it using when the kernel is just the fundamental solution of the random walk, the probability to never return to A. It's the kernel, very nice. So that's the classical notion of capacity. But this is not what we want. What we are working with is the once capacity, which I define in a similar way. Except I'm not really defining it. I'm not going to give the exact definition of escapes, but it's pretty similar. It's a bit more complicated than that because you have to keep in mind that we only know what happens up to time t, and we are only interested in what happens in a box of size R. So R and T somehow come in, but let's not bother too much about these details. Um, the definition is analogous, but it depends on T and R. And so what I want to explain to you so you want to do not visit it, but not never, just first of all, only up to time t, because anyway, we can control anything up to beyond time t, so you just and then there are other conditions which are way too technical to explain why they come, but wait, the nature is the same. You don't return to, in particular, you don't return to A up to time t. But there are a few it was convenient to add a few more conditions, but we don't, we, we don't, it's not necessary. Um, you also wanted to escape a box of size R up to, so one of the conditions that I didn't write is that R up to, after time, for example, 100 R square up to T does not intersect the box of size R that we are looking at. But yeah, but you know, it will be it will be clear in a second. Okay, the role of R will be clearer once I state the first thing that I want to say about capacity. Ah, but it will still be here. Okay, but I still think that's not a, that would actually make my life easier. Except I have to fish all the pens from me. So, so here is the first lemma. So the first lemma says that this one's capacity cannot be large. So let me state it essentially formally. The probability that the one's capacity of, let's say we make the induction assumption that time t minus 1. Not, and we want to prove them for t. So we look at the one's capacity of our process intersection x plus minus r to the d. So I think that may be, okay, should I put, yeah, let's put parentheses here. And I want to show that this is in fact essentially r squared. So what do I mean? I want to show that the probability that this is bigger than r squared log to the fourth r is e2 minus log to the 3r, log to the 3t. So let's look at that for a second and try to digest this. So this is for Eugenia's question. Here is where R is important, actually. It's also true that I put it there, but I actually regret saying that because it's really not important. The point is that I want to estimate the capacity in a box of size R. Okay? So be careful between the two completely different appearances of ones here. First of all, there is the ones itself, and then once is used to define the capacity, but that's like, in a sense, two different things, right? I could measure the capacity. This here, it's just a set. So I'm looking at the set. I'm saying, okay, of course, the lemma, which is essentially triviality, once you get beyond the definitions, the lemma, of course, uses that in the proof. But in the statement, you don't need that. In the statement, the ones give you some random set, you intersect that with a box, and then you measure some capacity with some kind of kernel, which is very, well, it's not a kernel capacity, but okay, whatever, some property of the set, which a priori is independent. Okay? So for each x, yes. So for each, these kinds of, because the probabilities are so small, I can sum over x, or I can put the for every x inside the probability. It doesn't matter. And you notice that here there is also already an increase in the probabilities, because I'm getting actually much better probability than what I need, which is just t plus 1 or something. Okay, so that's the lemma. Questions about the formulation? So again, you take this set, you consider it just as a random set, intersect it with a box, sum the escape probabilities of the same process, but somehow an independent copy of the same process, if you like, and say that this is the typical behavior of random walk. R square is a typical behavior of a capacity of random walk in dimension 5 and above. So this is what you expect, and you see that I get it with relatively small error. Okay, so let's prove this lemma. It's actually, as I said, once you get past the definition, the proof is a triviality. Okay, fix some p. And now I'm saying it as follows. This incredibly long formula I'm going to write now is the whole proof. You look at the number of times such that if you start once reinforced from where you are right now, but again, it's an independent copy, that you escape your past. So notice the difference between the small t and the capital P. Okay, so this certainly is a mouthful, this formula, but it's the whole proof, basically. So let's see what's happening here and why this is actually a triviality. All this, what's happening? You are walking. You stop at some time t. You look at where you are, and you say, okay, what's the probability that I escape my past? Okay, I'm saying, okay, let's assume that the probability is bigger than p. If this probability is bigger than p, then every 1 over p times that this event happens, you actually do escape your past. Right? This is the only thing here. So every 1 over, if the probability is bigger than p, then every 1 over p attempts, they are essentially, you have a lower bound for the probability, so the probability that in one of them succeeds is like 1 over e or something like that. Okay, and if you go for more, then the probability that you don't escape in none of them is exponentially small in this parameter. This is just lambda is just a parameter. Okay, so that's the only point here. Right, so the R square is just because you don't know if you escaped or not before R square times happened. Okay, because we are looking about escaping this with intersection, the box. So the R square is just because you need the R square to know if it happens or not, and then it's just independent trials. So that's the whole. So that's the whole proof of this formula. Okay, and the lemma follows from the formula because you take lambda to be log to the cube, and then you sum over p in scales. That gives you that explains why it's a log to the 4th, right? Rather than a log to the 3, because you have to sum over p in a sequence of scales, and that's it. So the lemma is quite easy, but very confusing. I'm well aware of that. So please feel free to ask questions at this point, because we will still, almost no matter how many questions you ask, we'll still have time for the second lemma, I planned. Okay, so that's I am not using step 1 here at maybe I use only to say that after R square times I typically escape the box. So I'm using here H1, but not more than that. So yes, I'm using a little bit of Wonderwalk-like behavior, but not much more, because H1, let me remind you, if you sum it over a box of size R and you're at time R squared, then you are already outside of the box with positive probability. So that's the only use here.
The outside probability is this independent copy of the same once.
Yes.
The outside P.
Yes, there are 2 random walks here in this formula, right? There is the outside one and there is the inside one, which and this is this one, right? So let me call it omega prime. This is like,
This
yeah, but this is this, yes.
right. This is the P. Which one is over there? This one.
I'm just saying, if there is a probability P to escape your past, and you tried 1 over P times, then you will escape your past. But in order to ask if there is a probability P to escape your past, you have to use the second walker in some vague sense. So I'm not sure if it's clear or not, but But whatever, anything that happens with probability P and you try it enough times, it will happen. But you have to know that the probability is. So I don't know if it's worthwhile to really discuss if it's the first, if it's the same worker or not. It is a bit meaningless, I think. I'm saying if this happens with probability P, then you try it enough times, then it happens. Okay. And now the second lemma that I wanted. So let's hide this from the people in the Zoom. But before I hide this, let me remind you again what we want to show. We want to show that our worker inside a box is not too large. We already know that the capacity is not too large. We need to translate a capacity estimate to a volume estimate. And this is a very classical thing. Uh, It won't be very, as I said, these are relatively generic arguments for reinforcements. And so our proof doesn't work for linearly, but not at this point. No, at the point that I didn't, at a this would apply also for once, and yeah. And for linearly, yes, no problem. And also the next thing that I want to say will also apply for linearly. Our proof failed for linearly in a rather technical point. Well, they fail for R very small. Okay, so let me remind you just a classical fact about random walk is that the capacity of A is bigger than A to power 1 over 2 minus T. Okay, so even if you got completely confused at the last part, now I'm going to show you a classical fact about random walk. You don't need to have listened to anything in the last 1 hour and a half to understand this part. So I'm sure that's a consolation for at least part of the audience. Well, I'm not saying it won't help you understand how this fits in context. I'm just saying that this fact is a fact for simple random walk, so let's just prove it. No quote this time, a real proof. Okay, so let's see how this is proved. So let's start with A, actually. A, you will certainly agree that this is sum over all A in A of the probability when you start from A. I'm writing 1 in a very long way. Exits A. So I'm not saying that it escapes A immediately, just that at some point it exits A. Okay, since we are at least in 3 dimensions, then the walk is transient, so it exits any finite set eventually. So these probabilities are always 1, and the size of A is equal to this sum. Okay, now let's break this event according to the time and the place where you exited. Okay, maybe first the time. Sure. Of simply the probability that it actually exits at that t is exactly the last time that it was in A, and that point is B. So let me write it already in two steps. This is the probability of A that R of t is equal to B times the probability when you start from B that in fact you escape A. Okay, so notice the difference between exit and escape. Right, exit is at some time, escape is as before, immediately. So B is the last point. Okay, so this is, again, it's an equality, so it's trivial. So if it exits A, there must be a last time. I'm calling the last time that it's in A, T, can be any number, including 0. And then that means that it's at that time still at B, but after that time it's no longer at B. But since random walk has the Markov property, that means that I don't have to write it as R of t equal to B and R of t plus 1. I can write it as immediately as a product of two probabilities.
Escape, but by saying escape, you mean immediately.
Yes, in this sense. This is escape. Yes, yes. As is written over there. Okay, now of course we rearrange it. And now we just sum over A in A and T of this probability. Now, let me write it as two sums. Sum over T, sum over A. Now, I'm saying that the sum over A is smaller or equal than the minimum of 1 and A T2 minus D half. That's the first inequality. So that's the first time when something happens. Why 1? Because you reverse time. So starting at time, t is fixed here. So starting from A and being at time t is B is like starting at B and being at time t in A. And of course, you're at 1 point. Right? So you can't be more than 1. This sum cannot be more than 1 because the sum is the sum of probabilities of disjoint events. So they sum to less than 1. And this comes just from the size of the set times the probability to be at any particular point. There is a constant. All constant, by the way, can depend on the dimension. Okay? You sum over t, these numbers, you take exactly a to power 2 over d, put it on the other side, and the proof is done. Okay, questions about this proof? Yeah, yeah, yeah. Yeah, and when you apply to once, then here you have a problem because this is no longer the probability to be you have to justify this. And this is, and here, yes, you need a lot of random walk-like behavior to justify this step for once. This for random walk is it's a complete proof. Nati is already jumping ahead how to make this work for once, and for once you do exactly the same proof, but you have to justify this part, and that's like 4 pages and uses a lot and uses a lot of stuff from here. So this is the like a crucial point. But you're right that, as I said, these are pretty generic arguments for interacting random walks. You need some kind of past, you need that if you don't hit your past, you are independent from it, but that's most of what is needed for these parts. Okay, any further questions? So I think I don't have time for anything substantial, so let me just explain the why 6 dimensions. Because I only explained why 5 dimensions are necessary, but I didn't explain why 6 dimensions are necessary. And this is exactly comes from these two facts. Let's see what happens in 5 dimensions. If d is equal to 5, our estimate for the capacity is r squared. That doesn't depend on the dimension. But when you get from that the volume estimate, what you get is 2 divided by 1 over 2 over d. You get 10 over 3. That's more than 3. So this is set for which you know that the size... sorry. 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 The random walk intersection with a box of size r this is everything, say, up to logarithmic factor, r to 10 over 3, in dimension 5. That's what you would get in dimension 5. Because this was for the capacity of this guy. Translating capacity to volume, you would, okay. You would have to divide by 1 minus 2/5, which is 3/5, so it's times 5 over 3, so you get 10 over 3. That's more than 3. So it's hittable by a second random walk. A set for which you only know that its size is 10 over 3 is hittable by a second random walk. The condition to be unhittable is to be dimension size at least d minus 2. D minus 2. D minus 2. That's why the argument doesn't work in 5 dimensions. In 6, you're already good. This is still R2. This now becomes smaller, right? Because you divide by 4 over 6 instead of a 5 over 6, so you get the same thing is smaller than R to the 3, but also your requirements are weaker because as long as you are smaller than 4, you only need smaller than 4. So I think, so that's why we need 5 dimension. Here actually, 6 dimension, yeah. So here actually, let's write 3 halves rather than 2 halves. So this is the size that we are trying to prove. The size that we can get from the capacity argument is in fact 2 over 1 minus 2 over d, and at any dimension bigger than 6, you would be able to get this inductively because this is smaller than this, and you would be able to conclude 1 from this because this is enough to be unhittable in dimension 6. So that's why we need an extra dimension above the natural limit of these techniques. It's even a weakness that we roughly know how to work around, but it would make the proof even more complicated, and we didn't want to, but no, 5. 5 you need. For this kind of argument, 5 you definitely must. That's why we didn't bother. If we could do the exact critical dimension, that would be worth an effort. But to correct one incorrect dimension to a different imprecise dimension, where the difference is only 1, correct 6 to 5 when the answer is 3, that's not worth another 5 pages of proof. Okay, that's a question of taste. Okay, I agree. Anyway, we decided not to do it, but but you can't go below 5 because 5 is crucial for these kind of arguments because otherwise you just don't have this relaxed times at all. So yeah, I guess that's what I wanted to say.
Very much. Question?
Sure, sure.